young group. And then I'll talk about this nonlinear and quantum ops with structured light. So let's do it. These are the sponsors and the funding agencies. Very hard nowadays, but it's still alive. So let's move. So I like to show this slide here, especially international conference, showed people where Brazil is and where Florianopolis is in Brazil, Floripa, and where the university is in the island. So as you know, Florianopolis, most of the city is in an island. There's a small part in the continent. And then the university is located in the island, and is more or less this region here, this triangle. Is, you know, Floripa is a very pleasant place. So you are all invited to come here when it's possible to travel. And here's a picture of our research group in Florianopolis. It's called a group of quantum information in the south. This is an old picture, so some relatively old picture, because in the last months we have not been able to make pictures to stay together. So some people has already gone and some new people has come, but it's more or less this number of students and professors. And so we cooperate a lot. So we have a long list of collaborators here in Brazil and in several other countries. And we have, so I moved to Florianopolis 5 years ago. I was previously in Federal University of Rio de Janeiro. And since I moved to Florianopolis, I'm starting a new laboratory on quantum optics. So this is a picture of our 2 optical tables. So we are struggling to increase our experimental facilities. And these are views of some of our setups, just to have an idea. So in optics, is always something like this, an optical table. This is screws and things and then mirrors, etc., and lasers. And then I'll try to tell you a little bit about something that we've been doing here. So I'll start by talking about what we call the structured light. So it's a long history, and just to make it shorter, I can suggest to the people which is more interested this very recent kind of diffusion paper, which from Andrew Forbes is a collaborator from South Africa. And in fact, the idea is that structured light is light that you prepare. So you handle this, some of the degrees of freedom or more than 1 degree of freedom of light, and you tailor it for a given purpose. Okay, so then you can shape, you can design the state of your light field, for instance, in frequency, in time. But here in this seminar, we'll be interested especially in the transverse spatial degrees of freedom. So all of these things here are pictures of transverse profiles of light beams. And I try to show you how we can use these properties, these degrees of freedom, for many applications. So the motivations for studying this and developing this field is that there are many possible applications, starting from communication, of course, but to processing of information, and even for simulation, classical and quantum simulation. So this is what we call the structured light. So tailor some degree of freedom for a given task. So then I'll introduce a few concepts that will be important for us in this talk. So the first one is the concept of Gaussian beams. So Gaussian beams are light beams. For instance, the ones produced by a laser. So then if you look at the output of a laser, you will see a beam which always focus and defocus at some point. And the transverse profile is Gaussian. That's why we call them Gaussian beams. But in fact, there are families of Gaussian beams that we can prepare by tailoring the transverse spatial degrees of freedom. And we are particularly interested in two families of Gaussian beams, the Hermite-Gaussian modes and the Laguerre-Gaussian modes. So the first one here is like Hermite-Gaussian modes. So the electric field of the light beam is given by a function like this. So you have spatial envelopes where Z is the propagation axis, and X and Y are transverse coordinates. And then you have this, in the case of Hermite-Gaussian modes, you have this factorized functions, one for X and the other for Y, and the propagation phase. So, and these functions here, they are more or less complicated, but they have here this Hermite polynomials, and they are multiplied by these Gaussians here. One is real and this one is complex, which describes the phase of the phase of the wavefront. And then if you take a picture of this intensity distributions for these fields, you see nice pictures like this one. So they are families of modes, and they have these parameters, these quantum numbers, like 0, 0 is the Gaussian one, 1, 0, and so on. So these are modes, optical modes that we can generate in the lab. So the other interesting family is the Laguerre-Gaussian modes. So they are solutions for a wave equation, the paraxial wave equation, in cylindrical coordinates, which results in these modes with cylindrical symmetry. And they also have two quantum numbers, so the radial index and the azimuthal mode index. And the azimuthal mode index corresponds to an important property, which is the orbital angular momentum of light. It's a discrete property, and it's very useful if you want to encode information in these light fields. So then we have these two families of Gaussian beams. So they are light fields. And then we have this vector vortex beams. So then now we include the polarization in the game. And for instance, if I mix two light modes, they look like Laguerre-Gaussian modes. They are donut shaped like this. And with two different polarizations, then I combine them coherently. And then I have something like this electric field here, where you see that you have a coherent superposition. This is a classical field, okay, but it's a coherent combination of a spatial distribution with horizontal polarization and another spatial distribution that can be different from this one related to the vertical polarization. So then we say that we have a classically non-separable state in the sense that we have a combination of spatial and polarization mode, and whether the field can be found in this combination or in the other, and there's this phase between them. So in Brazil, we have a pioneer group in this kind of vector modes. is the group of Antonio Zalaquete in Federal University of Niterói, UF. And they look like this. If you take the transverse section of these modes, the intensity will look like this. So these are, for instance, the first order Laguerre-Gaussian mode is a Gaussian multiplied by the function r, the radial coordinate. So then you start from 0 and then you increase. So then you have something that we call singularity here in the middle. But besides of this donut shape, we have also a polarization state which changes depending on the transverse position. So then we can have this circular polarizations. We can have this linear polarization change in direction, which we call azimuthal distribution. And we can have also this radial distribution of polarization. So it's a very funny state of light. And but the fact is that if you can control, if you can properly prepare these states, you can manipulate two degrees of freedom. One is the polarization, is a two-dimensional degree of freedom, and the other is, for instance, the orbital angular momentum. So then it gives you a lots of possibilities in terms of applications. So these are the vector vortex beams. So the next stuff that will be interested is the parametric down-conversion. So the parametric down-conversion is a nonlinear process. So then I promised in the title that I was going to talk about some nonlinear optics. So this is a special kind of crystal called nonlinear crystal. And then if you send a laser, so the laser comes from there to here. If you send a laser, kind of blue or violet laser in this crystal, then there will be frequency conversion in the optical region. So then you need a nonlinear interaction to have this frequency conversion. And then you have this kind of color cone here. And then if you look at certain positions, you will find photons here, which are related by energy and momentum conservation. And we usually call them signal and idler photons. So then what happens here is that one photon from the pump beam is down converted into two new photons. One is the signal and the other is the idler. So it doesn't matter which one you call signal or idler. But so their energies sum up to the pump energy. And because of the momentum conservation, you have this structure. So if one goes there, the other one comes here. Kind of, it's not the same angle, but there is a proper angles that are determined by this momentum conservation. So I give you here two interesting references. This is a theoretical one by a Russian guy called David Klitschko. And this is a experimental reference, the first guys that analyzed experimentally this process. So this process here happens spontaneously. So this is spontaneous emission. So that's why, in general, classical nonlinear optics cannot explain this photon emission here. We need quantum optics to explain because there is spontaneous emission. But then you can also stimulate this emission. You can seed one of the modes. So what's the meaning of this? So we call this parametric down-conversion, so stimulated parametric down-conversion, StimPDC. And the idea is that I take another laser, a second laser, with the same wavelength of the light that is coming this direction, and I align them so that I have a good mode overlap. And because of this mode overlap, the stimulation, the emission in this mode is stimulated by the presence of the other photons here. So this is typical stimulated emission. And as a consequence, the idler beam is also enhanced, the intensity of the idler beam is also enhanced. So indirectly, the emission is also stimulated. And there are interesting properties of this idler field that comes from the seed and the pump beam. So this process here is like interaction between light fields mediated by the nonlinear crystal. So this is one of the things that we are going to use together with this structured light. So next topic. So then, so far I talked about these Gaussian beams, these vector vortex beams, parametric down-conversion, spontaneous and simulated. Now I'll talk about this two crystal sandwich source. This is parametric down-conversion, but then I use two crystals here. And why? This is because the parametric down-conversion depends on the polarization. So for instance, if I pump with vertical polarization, I produce signal and idler with horizontal polarization. This is a possible process. And if I want to analyze interaction between light beams like this one here, but which can be independent of the polarization, or in other words, I want to allow them to have any polarization state. So then one way of doing this is to use these two crystals. And in one crystal, I have a conversion like vertical to horizontal. And in the other crystal, I have horizontal to vertical. So the coherent combination of these two processes results in a process which is I can pump with any polarization states, and I can have signal and idler with any polarization state. So this kind of source was conceived to generate this Bell states like this one here. This is one of the Bell states in which you have a quantum superposition of two photons with horizontal polarization and two photons with vertical polarization. This is the so-called Bell state, and then they produced they invented this source in order to violate Bell inequalities using this source, etc. So then we have here an entangled state. But then, so this is highly quantum stuff, right? But then what happens if I stimulate this process? Then the quantum properties, they disappear because we have a deterministic stuff. And then, for instance, if I stimulate with a seed beam with H polarization, then I will produce an idler beam with H polarization. If I stimulate with vertical polarization, the idler will be vertical polarization. So the fact is that when I stimulate, it's like it looks like this seed beam here performs some kind of projection in this Bell state. Okay, and it's not only seeding with horizontal and vertical polarization. This thing can be generalized. So then I can write the same state here in terms of general polarization states characterized by this theta and phi angles and this alpha polarization state. This is just generalization of a polarization state, okay? And I can seed and pump with arbitrary polarization states. And for instance, if I seed with this guy here, theta phi, then I will have the idler in alpha. If I seed theta phi orthogonal, I will have in beta. Okay, so this is a process that we use. And the nice stuff here is that we can work with any polarization state. And this is important because we want to work with those vector vortex which have polarization distribution, so several different polarization states along the transverse profile. And the last stuff is a technical stuff, but I think it's interesting to tell you that we have this device here. It's called a spatial light modulator. The spatial light modulator is this screen here. This is an LCD screen. And you plug this thing in the computer, and you project some images here, like a monitor, a screen monitor, right? But the point here is that each pixel in the image that you project will apply a different phase in a light beam that is reflected from it. So then I can program here complicated patterns of different phase distributions, so that when I send this beam here, the transverse phase distribution of the beam will be modulated. So it's a transverse phase modulator. And using this kind of device, we can manipulate very well these transverse degrees of freedom of light. So for instance, I can send a Gaussian beam, zero-order Gaussian beam, and in the output, I can produce this Laguerre-Gaussian beams, for instance, among many other possibilities. So then we are going to work with these guys. And now I'll talk about our first experiment. But then I need to introduce you an old idea, which is the idea of optical phase conjugation. So the optical phase conjugation appeared very, very soon when they invented the laser in the 60s, and in the 70s, people were already doing nonlinear optics and studying nonlinear optical phase conjugation. So this is an old review, but it's very, very nice paper. So the idea is that if you take the electric field of the light and you write in terms of the complex representation, then you take the complex conjugate of the spatial envelope and of the spatial propagation phase, but you don't conjugate the frequency. So then you have something which is the time reversal of the beam. So for instance, I have this EC, which is, for instance, an input beam. And then I send it to some device, which is called the phase conjugation mirror. It's like a mirror. And this mirror applies an operation that conjugates these guys and turns into, in the output, another field, which has this envelope, which is the complex conjugate, and the K has also changed the sign. So if you compare this field with this one, you see that this one here is is a replica which propagates backwards in time. So this is very interesting stuff. Why? Because, for instance, if you have a light source, if you shine this light source in a mirror, ordinary mirror, and if it's diverging, and when it's reflected, it still diverges even more. But if you have a phase conjugation mirror, it reflects backwards, and then it converges back. It's very interesting stuff. And the same thing can happen with the polarization. So if you think about the polarization, for instance, a circular polarization, let's think about the left circularly polarized beam. Then if you send it to, let's see here in this picture, if you send it through an ordinary mirror, when it comes back, it's still turning, the polarization is turning in the same sense, but the wave vector has changed. So if it comes from here to there, so then when it's turning in one sense here, then it goes there, turning the same sense. But if you send it through a phase conjugation mirror, it comes back turning backwards. So this is the miracle of phase conjugation in nonlinear optics. And why this thing is interesting. So this is an example just to emphasize what happened, the difference between conventional mirror and conjugate mirror. So if you have a plane wave which propagates through a glass slab, then there'll be this phase that will be acquired because of the propagation in the glass. So then there'll be this step here. And then it's reflected in a conventional mirror and comes backwards. So it is 3 here. When it passes back in the glass, then this phase difference will increase. So the step is even higher, right? But then if you do the same thing in a conjugate mirror, then you see that the step comes back in the other side. And when it passes back to the slab, the operation is undone. So the phase acquired here is undone. Then immediately people thought about correction of wavefront distortion. So in this picture 3 here, if you send a plane wave through some turbulence, and then after that, you have a distorted wavefront, and then it's reflected by a phase conjugation mirror, comes backwards, and if this distortion does not change, it will be undone, and it will become flat again. So this is a miracle. Very, very nice stuff. And actually, there are lots of applications using this effect. For instance, to have very nice lasers, etc. So then, why are we interested in this kind of thing? This is because we are talking about phase conjugation mirror, but there is also the foregoing conjugation, which happens in our parametric down-conversion stimulated, because we can show that if we have this parametric down-conversion, and when we seed and we stimulate, we can show that the idler beam is the phase conjugated replica of the seed. So for instance, very funny effect that we see in the lab is that if we seed with the light beam, with the laser that is diverging, the idler will be converging, because it will do the same, it will have the same propagation properties as this one, but backwards. Then, so we have a phase conjugation process here. So what we want to do with this? We want to do the same kind of application, so corrections of wavefront distortions and so on. But before I show you what we have done with this thing, let me introduce these Stokes parameters. Stokes parameters is nothing but taking a polarization state and representing the polarization state in terms of a point in a sphere. So, and then the polarization state is characterized by 2 angles, which are related to the coordinates of this point in the sphere. So then you have, for instance, in the poles, it depends on how you define things, but for instance, you can have in the poles circular polarization, right and left. And in the equator, you can have linear polarizations like diagonal, horizontal, vertical, and so on. So I'm interested in these Stokes parameters because we can define phase conjugation in terms of these parameters. So then just have in mind that this is Stokes parameters characterize the polarization state. Now, let us think about this stimulated parametric down-conversion that I talked about. And then we have performed some calculations. We are experimental, but we do some calculations sometimes. And then in this work here, we calculated the polarization state of this beam here, which is produced when we have stimulated down-conversion with two crystals. And then there is the pump and the seed. And we show that the polarization state of this being here is given by this expression, which depends on the polarization state of the pump and signal. So this index P refers to the pump, and this index S refers to the seed, okay? So then we can write the polarization state of this light beam here in terms of the pump and seed beam. So because this is the result of the interaction between these two beams. And then we can see that depending on the state of the pump, if I did not seed, we can have different Bell states, okay? For instance, what we call this phi plus and phi minus, which is just the change of the sign. But then depending on the state of the pump, I can produce the idler in these two polarization states. And you see that in one of them, we have this minus sign here in the third component, S3. And depending on the state of the pump, we have this minus sign in the second component. This minus sign in the third component is the expression of the phase conjugation in the polarization degree of freedom, okay? So then we can show that depending on the state of the pump, we can have phase conjugation in the usual sense for the polarization. I mean, this guy is the phase conjugate of this one, okay? And we can have another stuff, which is the change of sign in the second component. It's similar to phase conjugation, but it's a bit different. But then we made the experiment. Here's our setup. Is more or less like you are seeing. Just we show here the polarization detection scheme with wave plates and polarizers and the CCD camera. And here we have this polarization detection scheme, lenses, and we have a photon counter. So we have counted photons in the idler beam. And these spheres here represent the state of the idler beam. So each point here represents the state of the idler beam in a given set of measurement. But then this is, for instance, when the pump is in the diagonal state, we see that the polarization state of the idler appears in the opposite side with respect to this plane in comparison to the polarization state of the signal. So this is a kind of geometrical way of seeing the effect of phase conjugation. So when you have phase conjugation, you see that, for instance, the idler is the phase conjugate of the signal. So then I will see the polarization state of the idler here and the polarization state of the seed in the opposite side, like a mirror reflection around this plane, okay? And, okay. But if I pump with, sorry?
Professor, no, just to remind you, you still have 10 minutes, okay?
Okay. So then I'll move very fast. So then if I pump with the anti-diagonal polarization state, then I will have the effect which is similar to the phase conjugation, but in terms of this geometrical representation, is a mirror reflection with respect to another plane, is this one. So then this is kind of new way of seeing this phase conjugation stuff. And in the end of the other step in this work was to seed the simulated process with this vector beam, and showing that we can have this phase conjugation even for this very complicated polarization distribution. So then we take the seed beam, we prepare in this radial state, which has this polarization along this radius, and we pass it through a wave plate so that some of the polarization states are turned into elliptical and circular polarization states. And then we seed, and we measure the idler beam. And we see that depending on the polarization of the pump, we have phase conjugation or not. So it's a kind of controllable phase conjugation for this vector beams. So then this was the result of this work here that we did the beginning of this year. So also in the theoretical paper, we have demonstrated, we have built a quantum theory for describing this process of the stimulated down conversion with two crystals. So then we derived a density matrix for describing the output state of this guy here when we have this complicated pump and signal beams. And that is, so you can, because of this, this field here has more degrees of freedom, a geometrical representation of this beam is more complicated, but it's possible to generalize the Poincare sphere even if we have this complicated polarization state. So it's called the high order Poincare sphere and the high order Stokes parameters. And now our last experiment was to do this stimulated process and combine several different vector vortex beams, pump and seed, and see what happened with the idler. So then we have this result here, which look complicated, but we have observed interesting effects. One is that sometimes, depending on the combination of modes, the idler is still an eigenmode of the paraxial equation, and sometimes it's not. So depending on how you combine these modes. This is one of the things that we have. So then this is a very new work. And well, I was planning to talk a little bit about quantum thermodynamics, but as I only have 5 minutes, I only mention for you that there is this study of quantum thermodynamics, which is kind of understanding the limits of how thermodynamics emerge from microscopic stuff and quantum systems. And so there are questions related to out of equilibrium physics. And there are some fluctuation relations that we study in order to understand the relationship between generation of work and generation of entropy in given thermodynamic process. And our business is to use something called the analogy between the Schrödinger equation in 2 dimensions and the paraxial wave equation. So the results of the paraxial wave equation are these Hermite-Gaussian modes and these Laguerre-Gaussian modes. You see that these are also the solutions for the 2-dimensional harmonic oscillator. So this is the eigenmodes. These are the eigenmodes of the harmonic oscillator in 2 dimensions. So then the idea is that we can use our light beams, our paraxial beams, Hermite-Gaussian and Laguerre-Gaussian, to represent eigenmodes, energy eigenmodes of the harmonic oscillator. And then using this analogy and this kind of representation, we want to study thermodynamics with optical systems, with light beams. And then we performed our work using only a laser beam. And then we tested this fluctuation relation that I showed. And I'll skip very quickly. And then now we are moving to quantum properties of these modes and how they influence in these fluctuation relations. And then we also demonstrate how to produce thermostates of photonic systems, thermostates based on thermal distributions for the orbital angular momentum of these photons. And finally, we tested the fluctuation relations using these light modes and this analogy when the process is turbulence, and when we send to the turbulence a pair of entangled photons prepared in these states, this Laguerre-Gaussian orbital angular momentum states. And then we found interesting stuff related to the characteristics of the process. And then we needed to use a generalized form of the fluctuation relation, which was derived for an arbitrary quantum stochastic map, which is a process which is not appropriated for the previous relation. And then we demonstrated that then it's compatible with the turbulence that we used as a process. So then I went very quickly. If somebody is interested in this particular topic, then we can discuss. Yes, and then of course we check the consistency of these generalized relations with the second law of thermodynamics. This is always must be consistent. So then to conclude, so we use this stimulated parametric down-conversion to investigate interactions between vector vortex beams. We demonstrate this phase conjugation of for these beams. And we want to use this phase conjugation effect to perform some kind of error correction in communication schemes, and also machine learning assisted pattern recognition, which is related to when you send information encoded in these degrees of freedom, you need to read it, and then you need to recognize this pattern. And then it's possible to show that if we use some schemes based on machine learning, it's possible to improve this detection scheme. And we studied the quantum thermodynamics using light and orbital angular momentum states. And it's also possible to use polarization and in the classical and quantum regimes. And the perspective now is to use this experimental scheme to study thermalization of quantum systems, which is a very interesting topic. And also try to implement some thermodynamic cycles like heat engines, for instance. So that's what we want to do for the future. So hope I can have you visiting Floripa at some time. And thank you very much.
Thank you very much, Paulo. Very good presentation. So now we have time for questions. If anyone wants to make a question. We have Gabriel Soares raising hand. So please, Gabriel Soares, you can speak.
Hi, Professor. Thank you for the lecture.
Hello.
And hi, you hear me?
Yeah, I can hear you.
Okay.
Go ahead.
What is this crystal you mentioned, nonlinear crystal made of?
Okay. There are several kinds of nonlinear crystals that have been developed since the 80s, 70s. And this particular one is called BBO, is beta borate, barium, etc. So it's a kind of a combination of materials that change the polarization, electrical polarization response of the material. So then you have a strong polarization effect.
Okay. Because I am from Universidade Federal Fluminense, and
okay.
And Professor Rosella, Professor Zelachetti has some crystals too, but I think he doubles the frequency of the beam. If I remember well.
Yeah. I know very well the Zelachetti, a very old friend, and but I think they use a lot there the KTP, okay, which is another nonlinear crystal, but it's more appropriated because sometimes he uses optical parametric oscillators. So you put cavities around the crystal.
Okay.
And then depending on the wavelengths that are involved, some kind of crystal is more appropriate because of losses, because of absorption, etc. Okay.
Okay, thank you.
You're welcome.
So now we have a question from Julio Cesar. I'm going to read his question because he's without microphone. So, Professor, could you explain a little bit what is a turbulence mask?
Okay. Yeah, this was in the speed of light, right? So, look, we performed this experiment here. In fact, this experiment we did not perform. This was performed in South Africa by Andrew Forbes. And what they done was they have this parametric down-conversion, and then you split here signal and either photons. So one comes here, the other goes there. And you have here and here this device that I mentioned, spatial light modulator. Okay, this is a mask where you send light, and each pixel will produce a phase shift in the light beam, in this point of the light beam. And then, for instance, if you prepare this mask to have these structures here, which are generated based in Kolmogorov turbulence theory, there are recipes to produce these things with some parameters, given parameters. So you have this comes from astronomy, right? So this study of turbulence, light propagating through turbulence, etc. So then you prepare this mask, and when you in the modulator, when you send the light, and the light is reflected by this acquired phase, it's equivalent to the light passing through the atmosphere and having these fluctuations in the index of refraction of the air, right? And then it simulates in the lab the presence of turbulence. But in fact, in our case, we are not interested in doing a good or bad simulation of the atmosphere, right? But we wanted to apply some process in our light field and analyze what's the work performed by the process in the light field. Why we chose turbulence? Because turbulence is very hard to describe theoretically. In fact, there's no analytical theory. So then you have to simulate numerically, etc. And then the idea is that we can do the experiment and we can obtain results which are hard to obtain theoretically, right? So that's why we use these turbulence masks here. It's okay?
Okay, I believe it's okay. Julio, if you have another question, Julio. Okay, okay, thank you. Now we have a question from Pedro, or it's already answered. Pedro, if you want to speak on the mic, please.
I see the question here. It's about describing a 3D potential with the SLM. Yeah, I see. Okay. I think I can answer this question. Probably no, but let me state the problem. So you take a light beam and you use this analogy where the Schrödinger equation is equivalent to the paraxial wave equation. And then because in the paraxial wave equation, you take the Z coordinate to play the role of the time, then you stay only with the time-dependent Schrödinger equation in 2 dimensions. So then within this analogy, we cannot have a 3-dimensional potential because the potential in this analogy is given by modulations in the index of refraction. Okay, so for instance, you can understand more or less like this. For instance, a step. Imagine of these courses of quantum mechanics, you have the step potential, right? So the step potential for light is an optical fiber. Why? Because the index of refraction inside the fiber is bigger than the index of refraction outside. So then you have a step modulation. Of course, there is this cylindrical symmetry, but if you take 1 dimension, you have a kind of step modulation of the index of refraction. So this is equivalent of a potential for the light, okay? In the analogy with the Schrödinger equation. But then you cannot do the same in the 3rd dimension because you use the z-axis to represent the propagation, represents the time evolution.
Okay, Professor, I believe we still have time for just one more question. If anyone wants. No more questions. So, okay, thank you again, Professor.
Oh, thank you all. It was a pleasure. Have a nice
all yours.
End of conference and a nice weekend for all of you.
The same for you, Professor. Thank you very much.
Tchau, tchau.
Professor Rogério?
Olá.
Bom, a gente pode fazer uns 5 minutinhos de pausa, talvez?
Acho melhor vocês fazerem um pouco mais, porque vocês devem estar super cansados.
Mais? Tá bom. Bom, acho que pode ser. A gente poderia testar, na verdade, só fazer um teste.
Tudo bem, mas dá um tempo pessoal descansar, dá uns 10 minutos.
Ah, claro. Ok.
Mas você quer testar? Vamos testar.
Tá.
Pronto. Certo?
Tá tudo certo. Ah, o full screen, eu não sei se... Porque às vezes... Ok. Tá bom. Ok. Obrigado. Então, a gente começa às 4h25.
Tá bom.
Ok.
Você está com uma cara bem diferente na foto.
O áudio não tá. É, meu cabelo também, né? Tá mais
Eu
alto.
cortei meu cabelo esse final de semana. Eu tava com há 10 meses sem cortar cabelo.
Eu cortei o meu próprio cabelo. Ele tava maior.